Hello everyone, in this video we'll be discussing 7.2, which is trigonometric integrals, and there's kind of a lot to discuss here, but I'm going to try to do my best to basically give us an example for each particular case. Now here we're taking a look at integrals of the form a power of sine times a power of cosine, so it's a very particular type of trig integral. And basically we have different cases depending on the parity of the powers. That is, if one of the powers is odd, could be both of them are odd actually, but if at least one of them are odd, we must consider some type of U substitution. And I'll talk a little bit more about that once we get into more examples. But just know that U substitution will be used there. And notice that we may need the Pythagorean identity, sine squared plus cosine squared is equal to 1. By the way, specifically what we'll need is a version of this that solves for one in terms of the other. In other words, we may need the fact that cosine squared of x is equal to 1 minus sine squared, or the other way around, sine squared is equal to 1 minus cosine squared. Perfect. And basically what happens in the particular U substitution is we want U to be the non-odd power trig function if there is a non-odd power. If they're both odd, then it doesn't matter which one you actually select. And we'll kind of see that with some examples. But here I say when, so this is when they're odd, when you have an odd one. But if they're both even and you have no odd power, then we must use the so-called power-reducing identities. Now you may actually know these so-called power-reducing identities by other names. Basically they come from the double angle formula for for cosine. So cosine of 2x is equal to something in terms of, well, it's basically cosine squared minus sine squared, but using these Pythagorean identities, you can actually rewrite that and get these two identities as a consequence. But notice that the benefit here of writing it in this form is it basically reduces the power from having a trig function with power 2 to now a trig function with power 1, but now the argument has changed. And notice cosine 2x here really means cosine of 2x. We just very often omit the parentheses. So just kind of keep that in mind. Now here, it may be helpful to consider this identity, which is actually a retelling of the double angle formula for sine, which is sine times cosine is equal to 1/2 sine of 2x. Great. So now let's take a look at this particular example. Notice we have a power of sine times the power of cosine, and we have an odd power. So what I kind of said earlier with odd powers is that if you have an odd power, then you want U to be the non-odd power if there is a non-odd power. So in this case, we want U specifically to be cosine. Now, basically the reason why is because we can actually take apart one of these signs and pair it with dx. So this is sine to the 4th times cosine squared times, think of this as sine of x dx on its own. And this helps because notice since this is they're only even powers here, if U is cosine, its derivative will be sine, and then sine to an even power you can write in terms of cosine, even powers of cosine. So we'll actually see that happen. And that will work the other way around as well if we had an even power on sine instead of cosine. So notice in this case, du is actually equal to derivative of cosine is negative sine of x dx. And notice what this implies is that negative du is equal to sine of x dx. And of course we have a sine of x dx right here. So we can now replace this with negative du. And that negative sign I'm actually going to pull out in front of the integral because it's a constant essentially. Imagine negative 1 times du. So I'm going to do that, pull the negative 1 out. At the same time, I'm going to consider the fact that sine to the 4th, let me kind of box the U substitution so we don't get too lost. So I'm going to write over here, sine to the 4th of x is equal to sine squared squared. And what's sine squared? It's 1 minus cosine squared, which is helpful to rewrite it in terms of cosine because that's our U substitution. We want to rewrite everything in terms of U now. So this is really 1 minus U squared, all squared, using our U substitution. Perfect. And of course, so that's handling this part. Now this part, of course, is U squared because U is cosine again. And then we have du, the negative we already pulled out. Now all we need to do is expand this out, distribute the U squared, and then antiderive each term using the power rule. So let me try to do that real quick here. So if we expand this out, we get this by binomial expansion. And again, let me kind of border this off. Du. Now finally distributing this u squared into each of these three terms, we end up getting the integral, negative the integral of u squared minus 2u to the fourth plus u to the sixth du. Then finally we can antiderive each term using the power rule. So we get negative the quantity u to the third over 3 minus 2u to the fifth over 5 plus u to the seventh over 7, close parentheses, and then add a constant c because it is, of course, an indefinite integral. Now finally we can replace u with what it was equal to, which is cosine, and then we'll basically be done. So I'm going to clean this up and write that out right now. Alright, so I've cleaned things up here, and now all I'm going to do is distribute the negative and rewrite these as coefficients, fraction coefficients, as well as replace u with cosine. So after distributing the negative and doing that, we get negative 1/3 cosine to the third of x plus, because the double negative, 2 over 5, so 2/5, cosine to the fifth of x, and then minus 1/7 cosine to the seventh of x, and then finally plus our constant c, and that'll do it for this problem. Fantastic. And now again, we're going to take a look at a few more cases of integrals of this form before moving on. Right, so here now we see an instance where we have even powers. In particular, we only have an even power involved in one of them, but if you wanted to try a product of two even powers, so sine to an even times cosine to an even, basically you would write one of them in terms of the other using those Pythagorean identities. And it's kind of easy to see that that will work because Pythagorean identities involve squares, which are even powers anyways. So again, that can kind of be done based on some ideas we'll be seeing here. So here, again, we wanted to use these so-called power reducing identities. And just to recall what those are, it's, well, cosine squared of theta is equal to 1/2 times 1 plus cosine of 2 theta, whereas sine squared of theta is 1/2 times 1 minus cosine of 2 theta. So the way I like to think of this is just that cosine doesn't like sine, hence the negative for sine. And besides that, they kind of look the same. So that's how I remember it, but you don't really obviously have to remember this. So we're going to apply this here. So I'm going to write this as 1/2, so pull the 1/2 out, 1 plus cosine of 2 theta, d theta, and the limits are still from 0 to pi. There's no change in limits because there's no substitution. And now we can just antiderive bit by bit. So the antiderivative of 1 with respect to theta is just theta itself. The antiderivative of cosine of 2 theta, I'll have to walk you through this, but basically it's a small u substitution and we can kind of do it in our heads a little bit. So we end up with 1/2 times the antiderivative of this is just theta. The antiderivative of cosine, recall, is positive sine. But since it's of 2 theta, we have to divide by 2 because of the chain rule, basically. So this is kind of like a small u substitution. So notice that if you were to call this u, then the antiderivative of cosine of 2 theta, if u is equal to 2 theta, du would then be what? It would be 2 d theta. So you see the 1/2 du is equal to d theta. So with that being said, you can replace d theta with 1/2 du, pull the 1/2 out, and then you end up getting cosine of u times du. And notice antiderivative of cosine is just sine. So this is 1/2 sine of u, but since u is 2 theta, this is 1/2 sine of 2 theta. So again, I'm kind of just doing it in my head as far as the inside is a function whose derivative is a constant. So for that reason, all we really end up getting as a consequence is just antideriving it, ignoring the inside, keeping it the same, and then dividing by the derivative of the inside because it's a constant. Now that trick only works when the derivative of the inside is a constant. So something you can kind of play around with if you'd like, but the idea is there. And then I would write plus c, but this is a definite integral, so we're going to go from 0 to pi, plug things in. So notice since this is a constant multiple, we can actually handle the evaluation first and then just multiply that result by 1/2. So really I can write it like this, if you like. Let me move that there. Yeah, good. So when you plug in pi into theta, you get pi plus 1/2 sine of 2 pi. Sine of 2 pi is 0 though, so our first term is just pi. minus, when you plug in 0, that's 0, sine of 0 is also 0, so you just end up getting pi anyways. And since it's all multiplied by 1/2, in reality, the answer here is really just pi over 2. Perfect. Now, for this next one, well, there are a few different ways of handling this, but one thing that comes to mind is that notice that this is not in particular the case we saw previously, at least directly. It's not of that form, because we have we actually have a non-trig function t multiplied to an even power of a trig function. So what we're actually going to do here is apply integration by parts, and in particular I'll be using the tabular method just to make this kind of quick. So recall, for tabular method we need a derivative column and an antiderivative column. For the derivative column, we'll start with, of course, what we want u to be, and if you recall from Liate, an algebraic expression would have priority to be u over a trig expression. So t is going to be our starting point here. Its derivative is 1, and the derivative there is 0. Then we're going to find the antiderivative of sine to the 4th of t until we match this. So with that being said, really we want to find the integral of sine to the 4th of t. So I'm going to do this again using this idea here. So I'm going to replace sine to the 4th. Notice sine to the 4th is really just sine squared squared. So we can replace sine squared with 1/2 times the quantity. And actually, you know what? I'm going to distribute the 1/2 in. So we have 1/2 minus 1/2 cosine of 2 theta. And then this is all squared. It's not theta actually, this is t. There we go. dt. And if we expand this out, we get the following. We get the first one squared, 1/4. 2 times their product. The product is 1/4 cosine of 2t, negative 1/4 cosine of 2t. Double that, you get 1/2 cosine of 2t. And again, foiling this out is not a bad idea as well. And then plus the last one squared, 1/2 squared is 1/4 cosine squared of 2t, and then dt. Now, each of these terms can be dealt with individually in not too bad of a way, but this one is a little bit of a pain. But notice this is just an even power of cosine to the 2, and we actually did that already, kind of. So we'll get there shortly, but for right now, let's just kind of consider this. So the antiderivative of 1/4 with respect to t is 1/4 t. Antiderivative of cosine of 2t is 1/2 sine of 2t, as we've previously seen. Since it's negative 1/2, it's going to be negative 1/4 in the end, sine of 2t. So let me just kind of talk us through that again. So antiderivative of cosine is positive sine, so it stays negative. It was 1/2, and since it's sine of 2t, we divide by a 2, meaning we get 1/2 times another 1/2, which gives us this 1/4. Okay, now plus. So let's kind of think for a moment here. So treat this as cosine squared of theta. Now the antiderivative of cosine squared of theta is this, actually. But notice this is cosine squared of 2t, not just of t itself. So I guess we would kind of have to do this on our own to figure out what that would be. But really it's just a u substitution to get to this, or I guess a theta substitution. So on separately, basically, if we consider cosine squared of 2t dt, and we use this theta substitution, theta is equal to 2t, then d theta will be 2 dt. All right, so what does that mean? Well, it means that if you divide by 1/2, then you get that 1/2 d theta is equal to dt. So we can replace dt with 1/2 d theta, and then replace this with theta itself. So we end up getting here is 1/2 the integral of cosine squared of theta d theta. But the good news about dealing with things this way is that we actually already know what this is. This integral, cosine squared theta d theta, we did in the previous example, and it was this expression here before evaluating. So it was 1/2 theta plus 1/2 sine of 2 theta. Now, notice first here we have this 1/2 multiplied in addition to this 1/2 that's already multiplied. So 1/2 times 1/2 will be 1/4. And since we have this additional 1/4 here, I know it's a lot, we end up with 1/4 times 1/4, which is 1/16, times this expression, and it's theta, but notice if we back substitute, theta is 2t, so that's going to be times the quantity 2t plus 1/2 sine of 2 theta, but again, since theta is 2t, 2 times 2t is going to be of 4t. Perfect. And since this is, let me see here, I guess we'd be done. Yeah. So it's a little crazy, just a little bit, and the reason why it's super, super, super crazy, maybe a little bit too ambitious to be quite honest, is because we kind of have to combine some things a little bit. I'm going to clean this up, combine this, and this is just this part right here, and then we have to find the antiderivative once more to get this. So this is kind of taking a little longer than I thought it would, but it's still good practice, so I'll show that right now. Right, so I've cleaned things up here a bit, and now if you distribute this 1/16, we end up with, well, this will be 2/16, which is 1/8, and 1/8 plus 1/4, 1/4 is 2/8, so 2/8 plus 1/8 will be 3/8, so I hope we don't mind that a little bit of skipping there. So this term and this term, after distributing, will combine to 3ht, minus 1/4 sine of 2t, plus 1/16 times 1/2 is 1/32, sine of 4t. Okay. So that's the second entry here. So it's again 3ht minus 1/4 sine of 2t plus 1/32 sine of 4t, which is pretty crazy. And even worse, we have to continue and antiderive once more to catch up to this 0. The good news here is that since there's no powers, to find the antiderivative of this is actually pretty simple. So if we want to find the antiderivative of this, we're just going to take the antiderivative of each term. So the antiderivative of 3ht is, well, consider its power as 1, add 1 to the power, divide by that power. So that's t to the 2 over 2, but 1/2 times 3/8 is 3/16. Okay. Antiderivative of sine is negative cosine, so the sign changes to positive. And its cosine of 2t, inside stays the same. But since it's of 2t, we divide by an additional 2. So multiplying 1/4 by that 1/2 will give us 1/8. And here, antiderivative of sine, again, is cosine. Negative cosine, so the sign changes to negative in this case. And since it's of 4t, we divide by 4, and we get 4 times 32 in the denominator, which is 1/28. Perfect. Well, kind of perfect. It's still pretty crazy long. So we get 3/16 t plus 1/8 cosine of 2t minus, so this is not to be confused with a square, okay, minus 1/128 cosine of 4t. Wow. So we have a little bit of cleaning up to do, because now what we're going to do is, again, apply the rule of tabular, multiplying these diagonally like this, changing the signs accordingly, and then finally we'll be able to use our evaluation, use our limits, and evaluate, and we'll be done. Right, so I almost missed it, but I forgot to write the square when I carried things over here to the tabular table. So now let's see if we can apply the rules of tabular. So we have that times t, and you know what, I'm actually just going to write it out like this. So t times this thing like that, and then minus this expression here. So I'm going to actually distribute the negative and change the signs of each term accordingly. So it's going to be negative 3/16 t squared minus 1/8 cosine of 2t, and then finally plus 1/128 cosine of 4t, and now this whole thing evaluated between our limits, which are 0 and pi/2. Now the pi/2 part actually doesn't get too bad. Let's kind of see what happens. So if we plug in pi/2, this is going to be pi/2 times this whole thing here. Now 3h times pi/2 is going to be 3 pi/16. And sine of 2 pi when t is sine of 2t when t is pi over 2, the 2's cancel, you get sine of pi, which is 0. Sine of 4t when t is pi over 2, similar story. 4 times pi over 2 is just 2 pi, sine of 2 pi is also 0. So the only surviving member for the first thing really is just this, which we can write actually as 3 pi squared over 32, which I'll do. Let me move that square a little closer. Perfect. So this is really just from the first term here. Then minus, when you plug in pi over 2 here, let's see, we get negative 3 over 16 times pi over 2 all squared, which is pi squared over 4. So notice 16 times 4 in the denominator will be 64. These terms will actually combine quite nicely if we get a common denominator, but we'll worry about that in a second. When you plug in pi over 2 times 2 is pi, cosine of pi is negative 1. Negative 1 times negative 1/8 is positive 1/8. And then here we get 1 over 28 cosine of 4 times pi over 2. 4 times pi over 2 is 2 pi, cosine of 2 pi is positive 1. So that's plus 1 over 28. Perfect. And then minus, so this whole thing is the first part, plugging in just pi over 2. When we plug in 0 now, well, the first term goes to 0 because we have times 0 in front when t is 0. And then here, this one 0 minus cosine of 0 is 1. So this is going to be negative 1/8. So minus negative 1/8 is the first surviving term, and then plus 1 over 28 is the second surviving term, because notice again, cosine of 0 is 1. Now this will actually clean up quite nicely if we distribute. Let me just make sure we have things correct. Good. So if we distribute, this becomes positive, this becomes negative. So let me just get rid of that. So kind of cleaning things up here. It's kind of not advised to erase as you go along because you may lose information, but I think we're going to be okay. Now notice we have 1/8 plus 1/8. The 1 over 128 actually cancel out. They seem kind of annoying to begin with anyways. 1/8 plus 1/8 is 2/8, which is 1/4. And this is going to be 6 pi squared minus 3 pi squared all over 64. And that's just, well, 6 pi squared minus 3 pi squared is just 3 pi squared itself over 64, and then plus 1/4. Nice. So actually not a bad looking answer. Pretty crazy. This problem was obviously a lot longer than I anticipated it to be, but believe me, you deserve to see something like this eventually. It wouldn't be a Calc 2 class without me showing you something as crazy like this. And now we're going to take a little bit of a turn. We're going to look at different forms involving trigonometric integrals. Right, so here is basically a parallel to the integrals of the form powers of sine times power of cosine. Here, of course, we have power of tangent times the power of secant. And similarly, I guess you can define something if you had a power of cotangent times power of cosecant. They behave very, very similarly, as it turns out. But we're not really going to be discussing those, to be quite honest. Those are kind of more oddball integrals. Here we say that if n, the power of secant, is even, then we let u equal tangent. But if the power of tangent is odd, then we let u equal secant, which is a little hard to remember. But to be quite honest, we have a better way of remembering this, just kind of what we saw when we took a look at actually applying the integral, the strategy I gave you for the integrals of sine times cosine, power of sine times power of cosine. I basically said you want to leave one of the powers off to the side, or one of the trig functions off to the side. You'll see what I mean when we get to this example. But both cases require this trig identity, this Pythagorean identity. By the way I normally explain this is true is just kind of consider the usual Pythagorean identity, sine squared plus cosine squared is equal to 1, and then just divide every term by cosine squared so that you get, of course, tangent involved, because sine over cosine is, of course, tangent. So notice what you end up getting here is tangent squared, the first term, 1, because cosine squared over itself is 1, and then 1 over cosine squared, of course, is just secant squared. So this is true based on the usual Pythagorean identity, and similarly you can find one if you divide by sine squared instead, that relates cotangent squared to cosecant squared. But anyways, with that said, let's see if we can figure out what we'll do here. Now, again, here it kind of says something about which one to use, but I'm going to try to discuss this in a more intuitive way. So basically we have two options. Either we can save secant tangent to the side, or we can save secant squared to the side. And the reason being is because recall that the derivative of tangent, so we'll write d with an arrow, so derivative of tangent is secant squared, and derivative of secant is secant tangent. So for that reason, we want to save one of these pieces off to the side to kind of act as our du for our u substitution. And notice, if we were to save secant tangent off to the side, well, that I don't think is a good idea, because if we do that, then we'll have tangent to the 5th theta, and then secant to the 3rd theta, and we don't have any even powers left over, so for that reason we can't actually use the Pythagorean identity to rewrite one in terms of the other. By the way, when I say both cases require this, one case will definitely require this to write secant in terms of tangent, or secant squared in terms of tangent squared anyways, but the other case would actually require us to write tangent squared in terms of secant squared. So that's just solving for tangent squared. But notice, since we don't have any even powers once we pull one tangent and one secant off to the side, that's not really going to work for us. So instead of pulling a secant tangent out off to the side next to d theta, we're going to consider what if we had pulled off a secant squared. So if we do that instead, so imagine getting rid of a secant squared and pulling that off to the side, we get secant squared like this left over, and then we're taking away a secant squared and pairing it with our d theta. That's secant squared theta d theta. There we go. And this works because notice this is just the derivative of tangent. So if we let u be tangent, then this is a good qualifier to be our du differential. Perfect. So now let's see if we can make that happen. So I'm going to erase this thought here. And now let's proceed with this u substitution. If u is equal to tangent theta, then du, of course, will be secant squared d theta. So this thought is seeming to work. And again, this idea that I'm describing to us basically encapsulates what this is trying to say here above. And notice we'll have basically, because this is still in the integral of u to the 6th, and then this is du. But now what's secant squared? Well, secant squared is tangent squared plus 1. Since tangent is u, this is u squared plus 1. So now all we have to do is distribute and then use power rule for each term. We get the integral of u to the 8th plus u to the 6th du. The antiderivative of u to the 8th is u to the 9 over 9. Antiderivative of u to the 6th is u to the 7 over 7. Then we have plus c because it's indefinite. And now finally we can rewrite in terms of our substitution, because tangent of theta, of course, is u. So what we end up with is 1/9 tangent to the 9th plus 1/7 tangent to the 7th, and then plus c. Beautiful. So actually it wasn't too bad as long as we can get the ball rolling. And again, it really just kind of depends on which derivative you can pull apart to still have powers that are even, so we can use the corresponding, or I guess the appropriate, I should say, Pythagorean identity to write things in terms of the same function. In this case, we could write everything in terms of tangent, because that's our u substitution in this case. Right, so now we're going to do an example of the other scenario, and then we're going to take a look at something a little different that hopefully we never actually have to use, but you never know. All right, so let's see if we can handle this based on our previous discussion. So we want to pull out either secant squared or tangent times secant. But remember, we want even powers, and if we pull tangent squared off, then we'll have tangent to the 5th. Sorry, if we pull secant squared out, then we have tangent to the 5th and secant to the 5th, and neither of those are even powers, so we can't use a Pythagorean identity. So for that reason, we'll actually try to pull out tangent secant, or I guess you can call it secant tangent. And when we do that, we actually have even powers for each of them, which is good. And again, we're going to pull, let's call it secant tangent like this, which is the order I'm used to seeing it, but it doesn't really matter. And notice this is going to be our du, because of course, well, that's the derivative of secant. So that implies that our u substitution will be u is equal to secant, so that du will be secant times tangent. Perfect. We box this, doesn't get in our way, and let's see if we can continue from here. So if u is going to be secant, then we need to, this is going to be u to the 6th, we need to write this in terms of secant. Now remember that tangent squared plus 1 is secant squared, so that means tangent squared is equal to secant squared minus 1. And this is tangent to the fourth, which is this squared. Since this is u squared minus 1, because secant u in this case, then tangent to the fourth will be u squared minus 1 all squared. Again, because tangent squared is u squared minus 1, but tangent to the fourth is that squared. It's tangent squared squared. And then times u to the sixth, and then times du. Perfect. Not too bad. So now all we have to do is distribute this u to the sixth, and this looks kind of similar to what we had previously. I kind of lied. We actually have to expand this out first. So if we expand this out first, we get u to the fourth minus 2u squared plus 1, then distribute u to the sixth. Perfect. There we go. And then back substitute, right, plus c, and game over. So we have u to the 10th minus 2u to the 8th plus u to the 6th, making sure we're good. Du, take the antiderivative. So we'll have 1/10 u to the 1/11th u to the 11th, because you have to add 1 to the power. And then this is going to be 2 over 9, because if you add 1 to the power here, you get 9. So minus 2/9 u to the 9. And then add 1 to this power, you get 7. So that's going to be plus 1 over 7 u to the 7th plus c. Rewriting u as secant, we're basically done. We get 1 over 11th secant to the 11th. X was x, yeah, good. Minus 2 over 9 secant to the 9th x, and then plus 1 over 7th secant to the 7th of x, and then plus c. Now these expressions we're getting as our answers, you may be able to use some trig identities to write them a little nicer, but it's already too much as is, so I'm just going to leave it as we've been leaving it, of course. So that should be okay. Now we're going to take a look at these, which, to be quite honest, are kind of special integrals. This one is kind of special, but it's not really super special. Because notice tangent is just sine over cosine. So sine of x over cosine of x. And what can we say from here? Well, notice that if we let cosine be equal to u, then du is negative sine of x dx. So if you do the u substitution, u is equal to cosine of x, then du is equal to negative sine of x dx. And we don't quite have negative sine of x dx, but we indeed have sine of x dx. So we can actually replace this with negative du, just multiplying through by negative in this substitution, just to kind of show you. And now, so this doesn't get in my way, I'll kind of box it here. And what we end up with is negative 1 over u du, because of course cosine is equal to u for our substitution. Now this is great because we know the antiderivative of ln of u, almost ruined the surprise, well I ruined the surprise. Antiderivative of 1 over u is ln of u. So it's negative absolute value of ln of u plus c. But of course, what's u? It's cosine. So this one's actually kind of cool to check, because since derivative of ln of something is 1 over itself, so 1 over the inside, so it's 1 over cosine, times derivative of the inside, which is negative sine, we get sine over cosine. Notice the negative and the negative sign cancel out. So it's pretty cool to check out if you like, but I'm not going to do it. I kind of just said it out loud. This one, people spend their lives, no joke, trying to figure out how to crack this. There's actually a few really intuitive ways, but we need 7.4 to discuss those. So instead I'm going to show you the kind of, I don't want to say lame solution, but it is, you'll see. So we're going to use the super obvious u substitution. U is equal to secant theta plus tangent theta. Yeah, it's actually not very obvious at all. So that's kind of the main bummer part about this. But the good consequence is the result is something that's kind of taken to be a fact, and usually people just don't even bother remembering it and just refer to integral tables, or some people actually do remember it. It's not too bad. It's basically ln of absolute value of this, and we'll see that right now, because du, of course, is derivative of secant and secant tangent, may not have space here, plus derivative of tangent is secant squared, and then this is all times du, d theta. And now, why is this an obvious substitution? Again, it's not an obvious substitution, but why is it even a substitution? Well, it's because Notice here you can actually pull out secant. So from this substitution for du, you can actually write du as, let me see if I have some space here maybe. You can write du as secant theta times the quantity tangent plus secant. Okay. And now what's the beauty of this? Well, notice that this is just u itself, secant plus tangent, only tangent plus secant. So if we divide this u to the other side, we get 1 over u du is equal to secant theta d theta. So what does that tell us? That tells us we can actually replace the whole integral with the integral of 1 over u du. So this is really equal to the integral of 1 over u du using our substitution. Kind of crazy. The antiderivative of 1 over u du, just like over here, is ln of absolute value of u. And then using our substitution, it's ln of this crazy thing that I probably don't have space for. Maybe have a little space below. So it's ln of absolute value of secant theta plus tangent theta, all in absolute value, and then plus c. Very careful to box this. And I barely made it on the screen. Yeah, this is kind of a known fact. This is kind of a known fact. And these right here are used to handle cases that go a little beyond the general form of secant times tangent. In fact, I'm going to show you one example where we'll actually use this. And again, hopefully we never actually have to use it, but it's something that we definitely have. It's kind of in our emergency utility belt pocket, so to speak. Anyways, let's take a look at that example, and that'll be the end for 7.2 finally. All right, so for this example, this is the integral of sine cubed of theta, and we're actually going to be handling this, believe it or not, by integration by parts. And we actually can't use tabular here because no part of this integral has a derivative that's eventually 0. So we're actually going to have to do it the usual way. So recall that for integration by parts, we need u and dv. So we need dv to be something we know the antiderivative of. I guess we can use secant squared because we know the antiderivative of secant squared is tangent. So that shouldn't be too bad, I think. U is going to be the other one, so secant squared times secant will be secant cubed, so it's going to be secant. And then du, of course, is secant times tangent. So let me just write that. Du is equal to secant times tangent, theta, and then d theta. Don't have space, it's fine. There we go, that works. So now again, recall that the integration by parts formula is u minus uv, I meant to say, minus the integral of v times du. So that's going to be, u times v is going to be, let's see, secant theta tangent theta, minus the integral of, when you multiply v to du, you end up with secant theta times tangent squared theta. And should we use a substitution once more? Let me think for a moment. I think we're going to have to, because here if we pull out secant tangent up to the side, we have tangent left over, and secant tangent is the derivative of secant, not tangent, so that won't work for u sub. But actually what we can do is we can replace tangent squared, recall with the Pythagorean identity, with secant squared minus 1. Perfect. So now if we distribute this, we get secant cubed minus secant, which will look a little funny, but let's just kind of see what we can do here. I may have to clean some things up in a second. But anyways, we have secant tangent minus the integral of secant cubed, theta d theta. And then I would have, so I'm distributing this and splitting up the integral. So we have secant cubed minus secant, but distributing this negative amongst those integrals, we have negative secant cubed plus the integral of secant, which we actually know from what we discussed previously. So we know this, and we kind of know this, it's this thing. So this is kind of something that we saw a little bit in 7.1. So I'm going to say that this is actually equal to secant theta d theta, or secant theta tangent theta, plus the integral of this is ln of the absolute value of secant plus tangent, and then plus, or not plus, but it was minus, the integral of secant cubed. So normally the way we handle this is we call this integral I, and then we can solve for I. So I'm just going to clean this up real quick, add this to the other side, and then we'll have 2 times this integral. We can divide by 2 and then be done. Right, so I clean things up, and like I said, if we add this integral to the other side, cancel out here, we'll get 2 times the integral. So if we add shit down, we get 2 times the integral, but then dividing by 2 will just give us that the integral by itself is equal to 1/2 times this. I'm just going to distribute that 1/2. And again, since we have an indefinite integral, we need a plus c somewhere. So let's try it at the very end, of course. Secant plus tangent of theta. And that's our answer. Wow. A little crazy, but at least we saw an application of the integral of secant somewhere. And this, of course, is an honorable mention for scenario where you have a product of sine and cosine of different arguments, which we actually haven't seen in this section. We can actually use these so-called product to sum formulas. And I encourage you to try a problem on your own. You can just make things up like sine of 3x times cosine of 2x, for instance. And you can kind of see you'll use this where a is 3x and b would be 2x. And then you can kind of go from there. Kind of fun, but it's not something I want to spend too much time on. To be honest, you really don't see these too much at all. But thought I'd just bring it up because they are, of course, trigonometric integrals. So there we go. And again, that's the end of 7.2. Really hope you enjoyed this. It was kind of long, but a lot of chapter 7 is long. It's pretty fundamental because, again, we are starting to develop these techniques to take a look at all sorts of different types of integrals. Some can get kind of crazy. And in the next section, we're going to see some craziness, all right. So I'll see you in the next videos for that. Thanks for watching. See you then.